Glens of Tekoa Station. Ko whāruarua te monga, ko mandamus te awa. No America aho, ko Travis Horton toku inoa, o whare wānanga o Waitaha. G'day! Welcome to Glens of Tekoa Station. 422 Hill is the mountain, Mandamus River is the river. I'm from America. My name is Travis Horton from the University of Canterbury, and we're here to make a geological map. So if we're here to make a geological map, it's worthwhile taking some time to think about what our learning goals are. What are the things that we hope you get out of this virtual geology field trip? So our learning goals are, first and foremost, let's have some fun. We're going to try to have as much fun as we can through a virtual, digitally enabled learning experience. Secondly, we're going to recognize and record the structure, texture, and composition of common rocks. Third, we would like you to be able to accurately use correct geological terminology. And last but not least, you will create a geological map and cross-section. Here we are at outcrop number 1. We got 3 things to do. We want to describe the structure, the texture, and the composition of the rocks in this outcrop. So part of the structure, we always want to know where we're at. Where is this particular outcrop located in geographic coordinates? Where is it located in the landscape? And how is the outcrop expressing itself in the landscape? So we can see that this one is sticking itself out of the ground. But back to the first thing there, where are we located geographically? That will be provided by our handy dandy GPS unit. And according to the GPS, with an accuracy of 3 meters, at an elevation of 459 meters above sea level, the location is south 42 degrees, 45.926 minutes, east 172 degrees, 34.218 minutes. So that'll give us a geographic location for this outcrop number 1. But we're really more interested in its structure. Is it massive? Is it bedded? Is it fractured? These sorts of things. So we'll describe the structure of this outcrop, and then the texture and the composition. Those are things that you'll be able to do with photographs from this outcrop. So for the structure of outcrop number 1, we can see that it's sticking out of the land surface. It's pretty hard. So one aspect of the structure that we'll go through for all of our outcrops is how strong the rock is. Now the way geologists test that, by hitting the rock with a hammer. And based on how hard the rock is, what sound it makes, whether or not the rock breaks when you hit it with a hammer, whether or not the rock gets indented when you hit it with a hammer, if you can indent the rock with your thumb, these are all indications of how strong the rock is, which is related to the rock's structure. So this rock is very strong. The little hammer makes a pretty solid sound. So if we're really going to want to take a sample of this one, we're going to need the big hammer. So continuing with outcrop number 1 structure, we've got its geographic location. We can see that it's on the side of a hillslope. We know that it's very strong. Now, perhaps the most important thing to see about the structure of this rock is that it has beds. It's bedded. It has a layering to it, and we can see that there are shells in it. So there are fossils of old oyster shells, Austria shells. We'll get some close-up photos for you to have a look at those fossils in a minute, but because we can see oyster shells in it, in a bedded structure, we know that this is a clastic sedimentary rock. It's made up of broken up bits of shell and other rock fragments and little chunks of rounded minerals, things like rounded quartz pebbles, bits of clay mixed in there, the matrix, all kinds of things that are leading to this bedded structure. So for geologists, the key piece of information to get out of a bedded structure is its striking depth. I'm sure you're familiar with the right hand rule, but just to refresh it, we take our right hand, we go palm down, so the palm is down, we point our fingers in the direction that water will flow off of this bedded surface. So water is going to flow off in that direction, so I'm going to point my fingers in that direction. Now with my right hand, palm down, fingers pointing in the direction that which water will flow off of the bed, my thumb is pointed in the strike direction. So the strike of this bedded clastic sedimentary rock off in that direction over there. As geologists, we use a compass to measure that strike. We also use the compass to measure the dip. The dip is the angle below the horizontal that the bed is dipping, that the bed is inclined below the horizontal. So one of the key aspects of structure for bedded clastic sedimentary rocks, or any three-dimensional planar geological feature for that matter, we want to take the strike and dip. Here we are, outcrop number 1. And we're going to take our structural measurements, our strike and dip measurements of the orientation of this bed. Now, one thing that you also want to make sure you do in the field, whenever you have bedded plastic sedimentary units or bedded chemical sedimentary rocks, you want to measure the thickness of the beds. So this right here is one bed of oyster, shell, coarse pebble, sand, poorly sorted plastic sedimentary rock. It's roughly say about 65 centimeters thick, somewhere in that ballpark, 650 millimeters thick. Other beds within this same unit, same rock type, might be thicker, might be thinner. But we have beds of fossiliferous, oyster shell, poorly sorted, coarse clastic sedimentary bed up to about 650 millimeters thickness. The strike and dip measurement, our right hand rule, palm down, right hand, thumb is pointing in the direction of strike, the fingers are pointing in the direction of the dip. To get numbers for that, we use the compass. So Maddie is going to hold our trusty map board along the bottom edge of this bed, and I will hold the compass right up against the side, make sure it's perfectly balanced using the bubble balance, and then I'll spin the dial until the red magnetic arrow lines up with the red hollow arrow on the bottom of the compass, and I'll read the number off of the white tick mark. The compass has been set for the local magnetic declination here in North Canterbury, New Zealand. Then we'll spin it around and we'll take the dip measurement, but strike first. What's the strike of this bedded clastic sedimentary rock? So we got it level with the bubble. I spun the dial until the red arrows were lined up, and it is 075 degrees. 75 degrees east of north. So that's kind of east-northeast. That makes a lot of sense with where we're located on your base map. So the strike, the direction that my thumb is pointing when I use my right hand rule, is 075. Now the dip. To do the dip, I set the W west to being on the white tick mark. I'll put the edge of the compass vertically against the map board now, and then the little black filled arrowhead, that will be pointing to my dip angle. So I'm going to hold it up against that, and I'm going to measure the angle. Matt, you hold it nice and solid. Awesome, sweetie. Thank you. $60 degrees. It was a dip of 60 degrees. That's about right. From 0 down through 45 to about 60 degrees. So the strike would be 075 and the dip would be 60. And it's 60 off to the south.
Whoa, how concentrated is that ice?
It's just 10%. Kapai, outcrop number 2, quite a bit different from outcrop number 1. We'll do the location first, then we'll get into some structure, and we'll leave the texture and the composition up to you. So, location of outcrop number 2. We are 507 meters above sea level with a GPS accuracy of 3 meters. Location 42 degrees 46.093 minutes south. 172 degrees 34.164 minutes east. So that's our location of outcrop number 2. Structurally, we're on the side of a hill, or positionally, the context of the outcrop, we're on the side of a hill. It's a moderately weak sort of outcrop. It breaks relatively easily with light blows of the hammer. Not nearly as hard as outcrop number 1. It's also a lot darker brown, orangish, different colors. That reflects a different composition. The colors, these are all weathering colors. It's just iron oxide, different forms of iron oxide, but ultimately that's reflecting the composition of the rocks themselves. Structurally, there are beds. And when you look closely at these beds, I'll take some pictures for you in a minute, but when you look closely at them, they look pretty clastic, relatively coarse clastic. But the trick about this one, it's volcaniclastic. It's right on the boundary between an igneous rock and a sedimentary rock. So it's an igneous volcanic process that made a lot of the material in this rock. It blasted out of a local volcanic center. But then gravity allowed those volcanic bits, those clasts, to settle down, draping the landscape. In this case, getting deposited below sea level. They've been reworked by shallow ocean currents. There's a little bit of rippliness in here in these beds. So it's a volcaniclastic rock, right on the boundary between igneous and sedimentary rocks. Made up of volcanic materials, but deposited through a gravity-based sedimentary process. In our map units, Savon 1969 is one of your key resources, and Savon would have named this the Tekoa Tuff. So the type locality is right around here at Glens of Tekoa Station. So structurally, we've got these beds within a volcaniclastic unit. So we can take a strike and a dip on those beds. Intersection of a horizontal plane with the bedding surface. Spin my red so it matches with red. Horizontal. Go back just a wee little bit. Yep, I like that. Strike 2, 2, 3. 223 degrees is the strike. Now, right hand rule, palm down, right hand, palm down, fingers pointing down the direction of dip, the direction that water would flow off of the surface, and my thumb is pointing in the strike direction. Now, that way over there is north. Okay, outcrop number 3, 530 meters above sea level, 42 degrees 46.029 minutes south, 172 degrees 34.140 minutes east. This is a very strong but soft. I can scratch it with a hammer, so very strong but soft bedded carbonate. It will fizz when I put weak hydrochloric acid on my scratch marks. I'll make a short movie of that in a minute. But the thing we can do with these bedded carbonate rocks is take the strike and dip. Very crucial structural observation. So I've already done that for you. The strike here was 176, so it's pretty much striking to the south, off that way. Right hand roll, palm down, fingers pointing in the direction that water will flow off the bed, thumb.
Hit it. Oh, how you feel, brother?
Feeling good.
You feel good?
Feeling good. Improving.
Ain't so much bone, brother. How you feel, man?
I feel all right.
I call your name. I don't want no people to know you're in here. How you feel, fella? Hey, jam! Sure getting down.
Here we are at outcrop number 4, which looks a lot like outcrop number 1. But before we get into our STC, where are we? Handy dandy GPS is telling us we are at 454 meters above sea level with a GPS accuracy of 3 meters. The location given is 42 degrees south, 45.971 minutes. 172 degrees east, 34.047 minutes. So that's our location here of outcrop number 4. Now into the structure. Just like outcrop number 1, we've got a bed. We've got a 3-dimensional feature, a layer sticking out of the ground surface. It's a little bit harder than the rest. It's a prominent bed. So outcrop number 4 and outcrop number 1 have a bedded overall structure. Different to outcrop number 1. Outcrop number 4, this prominent bed is roughly 260 millimeters in thickness. It's a rough approximation, so not quite as big as the prominent bed at outcrop number 1, but it's a similar overall rock type. In fact, it's the same map unit. Now we'll be giving you all the stratigraphy for this area, and your main resource again is Savon 1969, a paper that goes through the stratigraphy of this area here at Glens of Tekoa Station. Strike and dip of outcrop number 4. We're going to start off estimating with our right hand rule. We've got this prominent feature behind the map board now. It's right hand, palm down, fingers pointing in the direction that the water will flow. It's going into the hill slope, so strike is off towards Maddie, and the dip is dipping off in that direction. So to get a number on those strike and the dip structural information, we take our compass, we hold the map board nice and firm, I get the compass balanced, and we spin the dial until the 2 red arrows are lined up. Hold that nice and steady. There we go. Good teamwork. And we've got a strike of 066, so 66 degrees east of north. Now our dip, spin it around. Our dip again, 60 degrees, just like outcrop number 1. So strike 066, dip 60 degrees to the south.
Cat asked me, say, are you somebody? I said, damn right I'm somebody. What do you say when I say, are you somebody?
Damn right I'm somebody.
Lynn Collins, Miss Collins, are you somebody?
Yes, I am somebody.
Well, she is. She's a lady. Thank you.
Right on.
Miss Ray, are you somebody?
Yeah, right.
Here we are at outcrop number 5. And just like my shirt, there are 2 different units here. Kind of a green and a brown. Well, here we've got kind of an orangish, brownish, grayish, and then a wavier, orangish, brownish. 2 different units. We're at what's called a gradational contact. 1 map unit below, 1 map unit above, and the gradational contact is in this area. So for outcrop number 5 here, the structure is very, very important. Structure is important because it's giving us a contact between 2 different map units. And our structural measurement, our strike and dip measurement of this gradational contact is going to be very important to our ability to construct and create an accurate geological map. First things first, where are we? Location, handy dandy. GPS tells us we are at 520 meters altitude with a GPS accuracy of 3 meters. Location is 42 degrees south, 46.026 minutes, and 172 degrees east, 34.037 minutes. So that's our location. The position of outcrop number 5 here within the land surface. We're a little bit higher up. We're still on the side of a hill slope. That hill slope is roughly north facing. And again, we have beds. We can see that there are layers within this unit that have a 3-dimensional planar orientation. This is a bedded rock. On the bottom, there's lots of little clasts, so it's a bedded clastic rock at least. And above, the beds are wavier, little lenses or like little ribbons. We call that ribbon bedding or lenticular bedding. So all kinds of interesting structural elements to the bedding within this unit, within the contact between these 2 units. So these ground layers here in the lower map unit, they're striking along in this direction. So right hand rule, right hand palm down, thumb is pointing in the direction of strike, fingers are pointing down dip. I want the intersection between a horizontal plane and this layer, which is representing the overall bedding. So I take the compass, put it up against that layer, make sure I stay on that particular layer, and I get the compass nice and horizontal. And I ever so carefully twist until I'm lined up. I'm happy with that. That's telling me my strike is 077. Yes, 077, 77 degrees east of north. Now for my dip, spin it around so I got the W on the white tick, read it through the back. Dip, I'm just going to take that same bed, project it along, get perpendicular to it as best I can. Don't fall off the mountain, Travis. Upside down, flip it over. This way. Now we got it right. .45 degrees, 045, 45 degrees again to the south. So our strike 077, dip 45 degrees to the south. It's important to get a three-dimensional surface to get those accurate strike and dip measurements. Another thing about the structure here, the strength. See if the microphone here can pick this up. Not nearly as hard as outcrop number 1. It's got some hard bits in it, but overall, it's kind of a dull wall. Moderately weak, moderately strong, somewhere in the middle sort of rock. Doesn't take much to break it off. Up here, it's harder. These ribbony or lenticular beds above us, it's dominated by the overlying map unit, which is a cliff former. It's the overlying map unit that's making the top of this ridge that we're almost to the very top of right here. So the unit on top is more resistant, and it's a harder, stronger rock than the unit underneath. Pretty soft. The hammer's scratching those lenticular ribbony beds pretty well. And it fizzes. Carbonate.
Phase 4.
Outcrop number 6, location 551 meters above sea level, 42 degrees 46.183 minutes south, 172 degrees 34.034 minutes east. 550 meters above sea level, 42 degrees 46.183 minutes south, 172 degrees 34.034 minutes east. That's our location for outcrop number 6. It's really just like outcrop number 5. It's the top unit at a contact between the underlying volcaniclastic unit and this overlying cliff or ridge forming carbonate, the neogene flaxdown limestone. That's what this unit is. Now, the neat thing about limestones, they tend to be cliff formers, ridge formers, all across the planet. So they're pretty strong. Very strong. That's the strength of the rock. The neat thing is that the minerals, the carbonates, calcite for example, that make up the minerals of the rock, the minerals are pretty soft. So I can scratch the carbonate minerals pretty easily. So it's strong but soft in a structural sense. We have beds, ribbon, lenticular, lens-like, wavy, ripply, however you want to describe it. There are beds, and we are at an overhanging area where the beds are dipping in that direction. So the strike is towards the camera. Right hand roll, palm down, fingers pointing in the direction that water will flow off of the beds. Water will flow that way. My right thumb with my right hand palm down will be pointing in the strike direction. So let's take that strike and dip. We get our structural measurements done and dusted. I'm getting a strike here of 236, 236. That's correct. North is that way. Right-hand rule. Strike is off to the southwest. The camera is looking to the northeast. Strike line should be off to the southwest, so 236 degrees. Now let's get the dip. "55 degrees to the north. 55 degrees north is the dip. So structurally, outcrop number 7. Not much of an outcrop, but it's a new one. Looks like the farmer's been doing some digging over here, trying to explore the possibility of making a watering hole for his cattle. It's one idea behind why he's digging a hole in the ground here, but what he's exposed is a rock that's pretty silty and sandy, and when you look closely at it, we'll get some pictures up close in a minute. Closely at it, it's got some really nice rounded coarse sand to granule or pebble sized clasts. So it's got some pretty diagnostic, well-rounded quartz pebbles in it. That is a big hint to what unit it is. New outcrops, perhaps the most important thing about new outcrops is locating them. 518 meters above sea level, 42 degrees, 46.330 minutes south, 172 degrees, 34.008 minutes east. So that's our location of this crucial outcrop. Not too much to say about it. It's not really strong. I'd say it's weak to moderately weak, somewhere in that ballpark. Nothing really to take a strike and a dip on, but ultimately it's very easy to walk past this kind of outcrop. But I've been here a number of years, and this is a new one. Thus, we really want to put it on our maps. Outcrop number 8. First time we are seeing the Cretaceous 97 million year old Mandamus igneous complex. So this is a ridge forming unit. It's pretty competent, pretty hard. And that has to do with the fact that it's been altered. So this was an igneous rock, crystallized largely some kilometers below the Earth's surface. Since that time, it's been altered. It's had hot fluids move through it, strip out some of the primary minerals, or at least get rid of their shapes and whatnot, make some secondary minerals. So when you can get a fresh surface on this, it tends to look pretty bleached. I mean, like a whitish color, a light whitish kind of color. Every now and then you'll pick out some nice shapes of large phenocrysts, large crystals within this igneous rock. And as those of you who've taken a mineralogy type course before, those larger, more rectangular, lighter colored igneous crystals, they tend to be the alkali feldspars. In this case, it's potassium feldspar in this mandamus igneous complex rock. And one of the reasons why we know that is because there's so much lichen. So in this context, this mandamus igneous complex rock is very strong, makes ridges. It was crystallized some kilometers below the surface, largely, but now it's here as one of the highest altitude rocks within our map area. So how did it get here? It's been hydrothermally altered, perhaps silicified during that alteration. It also has a fair bit of potassium in it, micronutrients feeding all these lichens. So these are all things that give you some clues about this mandamus igneous complex rock. It's 97 million years old. It is the second oldest rock within our map area. And its location, we are 535 meters above sea level. This is outcrop number 8. Latitude 42 degrees, 46.346 minutes south. 172 degrees, 34.270 minutes east. Structural terms, altered, extremely strong, or very strong, massive. It's got some fractures in it. They're relatively subtle in this particular outcrop. In other places they'll be a little bit more prominent, but it's not extremely fractured. It just has some localized fractures or cracks within it. But ultimately it's a pretty competent, pretty hard ridge-forming rock. Made it. Outcrop number 9, the highest altitude outcrop in our map area. We are at 589 meters above sea level. Location, 42 degrees, 46.424 minutes south. 172 degrees, 34.024 minutes east. 589 meters up, that's our highest point. This outcrop is an igneous rock. It's pretty resistant to erosion, so it should be pretty strong. Yep, that is an extremely strong rock. I am not going to do very well breaking it with this hammer. Structurally, there's nothing to take, strike, and dip on. This is a relatively crystalline igneous rock. It's got a lot of lichen on it. It's also kind of rusty. I'll tell you what, that hardness is almost certainly due to some kind of alteration, perhaps a silicification that happened, or a hot fluid with silica in it that helped harden the rock up. But ultimately, those are types of things that you'll be able to answer when you take a up-close look at a fresh surface, assuming I can find one, or create one, a fresh surface of this mandamus igneous complex, 97 million year old igneous rock. outcrop number 10. Here we are, top of a hill, on a ridge line. We've got valleys on both sides of us. Our location for outcrop number 10 is altitude 509 meters above sea level. Latitude 42 degrees 46.278 minutes south. 172 degrees 33.873 minutes east. GPS accuracy about 3 meters. Structurally, let's start with the strength of it. It's a strong rock. It's a very strong rock. That's why it's making a ridge. Structurally, it has wavy beds in it. Now normally, this is the trick of this outcrop. Normally, we'd say those are the beds in this particular chemical sedimentary rock, and we'd use our right hand rule, and we'd do fingers pointing down the direction that water will flow, and our thumb will be pointing in the strike direction. In fact, that is what we will do. The trick about this one, it's been overturned. That's the bottom of the beds. In this direction is the top of the beds. So it was originally like this, and it's been overturned. The beds were in there like that, and they've been pushed over. So now they're in there like this. Top is in that direction. Bottom is in that direction. So overturned beds is one of the key structures here, and that's a really important observation to make because something had to push it over. So that's something to be thinking about as you go through these outcrops. This is a marine carbonate rock. We'll show you some textural and compositional stuff here in a minute. But ultimately it was deposited below sea level. Here it is 510 odd meters above sea level. It's been overturned. There's some pretty serious compressional forces working on this rock, and we want to try to understand where those forces came from. Striking it down. .047 is the strike. And 51 is the dip. So striking the dip, 047 and 51. We'll do it as a normal way, but it's crucial to remember these beds have been overturned. Outcrop number 11. Not much of an outcrop. Most students walk right past this one thinking it's just colluvium or soil. Here's the soil profile up above. It's very immature soil. You might call it an entisol. But the chunks, these are actually bits of rock. If I can get one out, you can see that they're actually indurated. Not very strong. I can break it with my hands. Not really friable or loose either. It takes a real light pressure, reasonable pressure with the hands, light pressure with a tool to break it open. This is the youngest geological rock unit in our map area. So if you look at Savon, this will be the Paho siltstone. It's the only place that it outcrops. So here we are, outcrop number 11. Our location, 504 meters above sea level, 42 degrees south, 46.241 minutes, 172 degrees east, 33.882 minutes. So that's 504 meters above sea level, 42 degrees, 46.241 minutes south, 172 degrees, 33.882 minutes east. Outcrop number 11. Structurally, it's weathered. It's weathering like silt does. It's got kind of what we call a popcorn weathering, little flakes that look like little bits of popcorn. It's the way silty and muddy units tend to weather, but it actually is a rock. It's on its way to becoming soil. It is a rock. And we know from Savon 1969 that there are marine microfossils in this unit, and it puts it somewhere in the Neogene. So that's a relatively young marine siltstone. Structurally, there's not too much to say about it. We can't really see any obvious beds. The fractures are part of the weathering in here. It's probably expanding and contracting as it gets wet, part of that weathering process. But ultimately, yeah, you could call this weathered, fractured siltstone. No strike and dip can be taken because I can't really find any prominent, obvious planar three-dimensional features. This might be part of a bed, but I don't trust that, so we're not going to take the strike and dip on that. I'll take a picture up in this area for your textural and compositional observations. Outcrop number 12. Location. Elevation of 507 meters above sea level, GPS accuracy of 3 meters. Location in lat long, 42 degrees south, 46.168 minutes. Longitude 172 degrees east, 33.743 minutes. 507 meters altitude, 42 degrees, 46.168 minutes, 172 degrees, 33.743 minutes. 507 meters, pretty high up. So the location of this outcrop is, like all outcrops, really important. You can see by looking off on that side of the screen that there's a little valley over here. And this unit, it's pretty fractured. It's got fractures going this way, it's got fractures going that way. And the trick here is figuring out whether those fractures are using previous bedding. So the structure here certainly has to include a high degree of fracturing, but I'll just cut to the chase. This is a bedded chemical sedimentary rock. It's a limestone. I'll show that to you in a second. We'll scratch it, show that it's soft, and show that it fizzes. It's high up. So the location and its structure and its composition that gives us a sense for what type of rock it is really gives us a clue as to some of the events that had to happen. So this limestone is made up largely of marine organisms, calcium carbonate shells, if you will, of marine organisms. So just like my shirt with all the fish on it this time, we were below sea level sometime in the past. This particular unit is Neogene. It's somewhere in the ballpark of, say, 25 million years old. Don't really know for sure, but it's in that ballpark. It's a neogene flaxdown limestone, deposited below sea level, but now 507 meters above sea level. So thinking about the location and its structure and its composition holistically gives us a sense for what had to have happened over the last 25 million years since this limestone was first deposited. It's deposited below sea level, now it's 507 meters above sea level. It had to have been uplifted. So we use geological reasoning, we use inference and just geological common sense to start interpreting what had to happen to a particular rock when we're making these geological maps. So if this rock was deposited below sea level and had to be uplifted up to this 507 meters above sea level in the modern time over a time period of 25 odd million years, it almost certainly got deformed. It almost certainly got cooked up a little bit. Some pressure and temperature and some fluids were going through it, but it also almost certainly got bent and tilted and folded. So ultimately the beds in this area were originally horizontal and now they're tilted. Right hand roll, palm down, fingers pointing in the down direction, the direction that rain or water would flow off of these beds, pointing off in that direction. My thumb pointing in the strike direction. So we'll take that structural measurement of strike and dip. Really rough, because this rock has seen a lot of what we call diagenesis, diagenic alteration. So it's really hard to pick out some of these beds, and the fracturing kind of complicates it. Strike direction, it's basically straight towards the camera. This is a fractured bedding surface here, so I'm just going to basically pretend that that's the bedding surface. It's a really rough estimate. Should be pretty close though. Horizontal. (034). Strike direction of 034. That's assuming that this bed right here is horizontal, going off in that direction. Now the dip, spin the compass around, get the W lined up with the white tick mark. Dip here is about 44 degrees. 44 degrees to the south, southeast. So strike and dip, it's basically striking northeast, southwest, and it's dipping off to the southeast at 45 degrees. The valley over here, we're going downhill off in that direction. That's what we call a dip slope. It's along the dip of the beds. This slope out in front of us over here is paralleling the bedding planes of this limestone. So we have a dip slope helping create the topography. So we got the location, we've got some structural observations. It's highly fractured, it's got beds in it. We've taken a strike and dip measurement. How strong is it? Pretty strong. Outcrop number 13. Location. Plus or minus 3 meters GPS accuracy. Elevation 393 meters above sea level. Location 42 degrees east. 45.999 minutes. So 46 minutes. Call it good. 172 degrees east. 33.608 minutes. So that's our location, 392 meters above sea level, 42.45999 minutes, 172 degrees, 33.608 minutes. Outcrop number 13, location. Structurally, it's a bit of a mangy outcrop, but it's an important one. So the location of this particular outcrop is really worthwhile, really important to stop here despite the relatively low quality of the outcrop. It's relatively high up, but it's the oldest rock unit in the map area. So it's got some angular, busted up little bits, highly fractured, but it also has some chunkier, lighter gray, harder little bits, a little bit grittier, scratching on it. We've got argillite over here, sandstone over here. The bedding orientation is like this. Right hand rule, that's basically a contact between the argillite and the greywacke. Right hand rule, palm down, fingers pointing down the direction that water would flow off the unit, thumb pointing in the direction of strike. The trick here about that bedded structure and its orientation, we don't really know which way is up. So this particular unit, the oldest unit in the map area, it goes muddy argillite, greywacke, muddy argillite, greywacke, and there's little beds of each. The greywacke, the sandstone beds tend to be quite a bit thicker, big massive sheets of sand washing off the slopes of Gondwana sometime in the Mesozoic. And the muddier bits are perhaps the finer grained material that settles out. So if you thought about it in a grading upward sort of sequence, the coarser stuff should be on the bottom and the finer grained stuff should be on the top. That would be a graded sequence. However, because it goes argillite, greywacke, it's difficult to actually tell at the outcrop scale. So structurally, we can say that it's bedded, we can say that it's highly fractured. I don't see very much in the way of veins in this particular outcrop, but you will see veins elsewhere in this particular map unit. But overall, yeah, that's our structure. The texture and the composition will be up to you. Let's quickly take a strike and a dip on that contact there between sandstone and argillite. So we're going to take 180 degrees off of this, because I did it in that direction. 226 minus 180. Oh goodness, what's that, 46? Yeah. 046 degrees is the strike. Yeah, 56 degrees is the dip. Pretty high dip off in that direction, 56 degrees.
Give it up, fool for bum. 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 Give it up, fool for bum.
Outcrop number 14, location. Elevation of 353 meters, GPS accuracy of 4 meters. Location is 42 degrees south, 46.009 minutes. 172 degrees east, 33.393 minutes. We're also right on the edge of the Dove River. This is outcrop number 14. Structurally, it's quite a bit going on here, very similar to outcrop number 13, but just a little bit cleaner. This is the oldest unit in our mapping area. So if you look at your Savon 1969 reference, it'll tell you what this particular unit is, and it's also the same rock we see at outcrops 0, 13, and 14. It's the oldest unit. It's been through a couple different mountain building events. As a consequence of that, it's been baked up, it's been slightly metamorphosed a little bit, it's been pushed way down into the earth, and as it's been uplifted back again, it's fractured. So for its structure, we see a lot of fracturing, cracks within the rock. Subhorizontal fractures and some vertical fracturing or near vertical fracturing. That's what happens to a rock as it goes from being compressed, being uplifted, and the pressure gets released. It pops in a horizontal way and it pops in a vertical way. The rock is fractured, highly fractured, one of the key structures here. It also has bedding in it. That's one of the really subtle things within this. They're really big, thick beds. It could be on the scale of some meters. But we can see that over here, there's less little white stripes running through the rock. And over here, there's a few more little white stripes running through the rock. Those white stripes are veins. Those veins were made when hot fluids moved through these rocks when the rock was buried deep under the Earth's surface. Those hot fluids created quartz and calcite veins, but only where that fluid could get in. So there's a difference in the permeability between this side and this side. Subtle differences within the rock. That tells us that there's different beds within this particular rock. Beds that had a slightly higher permeability for fluids to get through and beds that had a slightly lower permeability. For this particular unit, those are sandier sandstone beds called greywacke beds. There's also argillite beds. Now, argillite, that just means mud rock. Argil, anything, just basically means it's got a lot of mud in it, a lot of clay in it, a little bit of silt in it. So argillite, mud rock. So here we've got some muddy bits and some sandy bits indicating the bedding is relatively vertical. Pretty hard, pretty strong. That's slightly weaker. This bit is a slightly, the hammer just bounces off the outcrop and it's pretty high ring to it when the hammer hits. It's a little bit duller. That's a sharper, harder kind of sound. Again, that's reflecting the different beds with the different permeabilities that have seen the different fluid flow conditions. This might have been hardened up while those hot fluids made the veins. So, okay, outcrop number 15. Here we are again on the side of a hill slope. But location, we are 431 meters above sea level at 42 degrees south, 46.248 minutes, 172 degrees east, 33.567 minutes. So that's 432 meters above sea level, 42 degrees, 46.248 minutes, 172 degrees, 33.567 minutes. So that's the location of outcrop number 15. Structure, side of a hill slope. We've got a layer sticking out of the ground up here with a slightly different color and a different overall look to it below. Very similar to outcrop number 1. So we've got a bed. It's a bedded feature. Got a nice bed up here with some other bedded clastic material beneath it. The prominent bed, the one sticking out of the ground, pretty strong. That makes common sense, right? Geological reasoning. The harder bits will be more resistant to erosion and mechanical weathering. They'll stick out of the ground. Down here, it's a duller thud. This is a softer, more erodible material. So that just confirms our structural observation that we have some beds here. Strike and dip. So this is kind of the bedding contact here, more or less in that direction. Zero, 3, 0 strike. So 0, 3, 0 is the strike, and the dip. .45 degrees. 45 degrees to the south or southeast. Again, a right-hand rule. Right hand palm down, fingers pointing in the direction that water will flow off the outcrop. My right thumb is now pointing in the direction of strike. It's middle of the day-ish. The sun is off in that direction. The strike is more or less off to the north-northeast. The dip is off to the southeast. That confirms, using our right-hand rule and the time of the day, the position of the sun, we can confirm that, yep, that strike and dip measurement for the structural observation makes some sense. How thick are these beds? That's probably about 30 to 40 odd centimeter thick bed. This one below, it keeps going down below the surface. That brings up an interesting point. How thick are these map units? You'll want to refer to Savon 1969. He's measured Savon and University of Canterbury second year students way back in the early 1960s, measured the thickness of a lot of these units, minimum thicknesses. So Savon 1969 has really useful information to you about the thickness of all these different map units. Outcrop number 17. 17. Where are we? We're on the top of a ridge, relatively steep slope, pretty high up. Elevation is 559 meters above sea level. That's 559 meters above sea level. Location is 42 degrees, 46.434 minutes south. 172 degrees, 33.908 minutes east. Structure. Outcrop 17 structure. It's pretty massive. Massive and fractured. It's very weathered or oxidized. It's got a lot of orange and reddish brown rust staining on it. It's got a fair bit of lichen on it. It's pretty massive. It is an extremely hard rock. That's why it's a ridge former. That's why it's way up here so high. Tell you what, this again is our one of our igneous units, part of the Mandamus igneous complex. So, structurally, massive, it's igneous, can't take any strike and dip on that. Could potentially take a strike and dip on the fractures, but we're not so much interested in the fractures, we're interested in the bedrock. So, texture and composition will be much more important on this outcrop.
I'm alright, nobody but about me. Why you got to give me a fight? Can't you just let it be? I'm alright, don't nobody but about me. You got to give me a fight. Why don't you just...
Such is the way of the world, you can never know just where to put all your faith and how will it grow. Gonna rise up, burning black holes and dark memories.
Outcrop number 19. Location. 416 meters above sea level. 42 degrees south, 46.346 minutes. 172 degrees east, 33.521 minutes with a 3-meter GPS accuracy. So 416 meters above sea level, 42 degrees south, 46.346 minutes. 172 degrees, 33.521 minutes east. That's outcrop number 19. Here we are again on the side of a hill slope. But this one's really cool and it's really important. Whoa! So I had to put on my party shirt. We've got a hard gray rock up above and a softer, more erodible, brownish, orangish, layered, potentially laminated rock beneath. We've seen this contact before. It's a contact between two different map units. We saw this contact before at outcrop number 4. Right, way back then. Outcrop number 4. Sorry, not number 4, number 5. Outcrop number 5. We've seen the same contact before. Contacts are really important structurally, so we want to get the location really nailed, and we want to describe the structure here pretty well. We've got a competent, stronger rock up above, and a less competent, weaker rock below. The strike and dip here, I've already done it, nice and simple. 045 is the strike, and 45 degrees to the southeast is the dip. Just to show you that, the contact is in here. Right hand rule, palm down, fingers pointing in the direction the water will flow off the slope. Thumb is pointing in the direction of the strike. The strike line there is 045, so basically northeast, southwest. And the dip angle is 45 degrees to the southeast. So that's our strike and our dip. Just to prove to you the strength of the rocks. That one's pretty hard. that was pretty weak. So strong rock, weak rock. We'll do separate textural and compositional photographs for the top unit as for the underlying unit. Again, this is a contact between a cliff-forming, ridge-forming strong rock and a more erodible, tuffaceous rock beneath.